We walk around our cities every single day, completely surrounded by these absolute giants. But the thing is, most of us have never even seen them. So today, we're going to go deep underground, and I mean deep, to uncover the massive, hidden structures that are literally holding up our world.
Seriously, have you ever stopped and just looked up at a skyscraper and thought, how? How does that thing not just sink into the ground? I mean, these are colossal structures, right? They're reaching for the clouds. So what's stopping all that immense weight from turning them into, the next Leaning Tower of Pisa? Or something way worse?
Well, the secret, as you might guess, isn't something you can see on the surface. Nope. It's a total marvel of engineering, a solution that's buried way, way down beneath our feet, and it's been perfected over centuries to solve this exact problem.
Okay, so to figure out how we keep these giants standing, we've got to start at the very, very bottom. Let's dig into the basics of the foundation itself. So right from the get-go, engineers have a pretty fundamental choice to make. If you're building somewhere and you get lucky, like really lucky, and the ground right at the surface is super strong and stable, great. You can just use a simple, shallow foundation. But what if it's not? What if the ground is soft or weak or it just can't handle all that pressure? Well, that's when you got to go deep. And this, right here, is where our hero enters the story, the pile foundation. Honestly, the easiest way to think about it is like a set of incredibly long, super powerful stilts. That's it. These long, slender columns, we're talking concrete, steel, they have one job and one job only, to completely bypass all that mushy, weak soil up top and transfer the building's insane weight way, way down to where the ground is actually solid and reliable. Okay, so we're putting the building on stilts. Got it. But how do those stilts actually work? I mean, how do they hold anything up? It's not as simple as just jamming a post into the dirt, right? Turns out, there are two really brilliant principles at play here. All right, so check this out. These are the two super clever ways engineers do it. First up, you've got end bearing. This one's pretty easy to picture. Imagine you're pushing a nail into a piece of wood and it hits a metal plate inside. It just stops, right? It's solid. That's end bearing. The pile is driven down, down, down until its tip rests on something incredibly strong, like bedrock. Simple. But then there's the other method, skin friction. And this is where things get really smart. Picture trying to pull a carrot out of the garden. It's kind of tough, right? It's not just the bottom holding it in. The soil is gripping the entire carrot. That's skin friction. The ground literally hugs the pile, creating massive friction that holds it in place. And a lot of the time, engineers will actually use a combination of both to get some truly incredible strength. Okay, so this is obviously a super powerful, pretty complex solution, which brings us to the next big question. When do you actually need to bring in this kind of heavy-duty engineering? And the answer is, well, in a lot of places. Piles are incredibly versatile. I mean, we see them supporting basically everything, from massive bridges that span rivers and crazy offshore oil rigs, all the way to simple retaining walls holding back a hillside. They're everywhere. But we can actually boil down the most common reasons into about four main categories. First, and this one's obvious, is for those massive structures, your skyscrapers, your heavy industrial plants. Second, anytime you're dealing with weak or just plain problematic soil, soft, squishy ground where a normal foundation would just fail. Third, whenever you're near water. Think about it. Riverbeds, seashores, currents can literally wash the ground away from under a structure. And finally, you've got special cases, like supporting a factory with equipment so sensitive that even the tiniest vibration could throw it off. So because the problems are so different, the solutions have to be too. This is not a one-size-fits-all kind of deal. Engineers have basically developed a whole toolkit, a whole menu of different pile types to perfectly match whatever specific problem they're trying to solve. And there are really two main ways to think about all these different options. First, you can sort them by function. What's its job? Is it supposed to bear a massive load pushing straight down, or is it supposed to hold back soil, kind of like a wall? And the second way to sort them is by the material they're made from. And that choice affects everything: their strength, how much they cost, and of course, how long they're going to last. The material choices are actually pretty cool. You've got good old-fashioned timber, which, believe it or not, has been used for centuries and is still fantastic for certain jobs. Then you've got the modern powerhouses, reinforced concrete and steel. These are for when you need just immense brute strength. And for the absolute most demanding projects, you can even use composite piles, which are basically a blend, combining materials like steel and concrete to get the best of both worlds. So, after all this, what's the big takeaway? What's the so what? Well, it's that pile foundations are so much more than just some boring construction technique. They're what we call an enabling technology. They're fundamental to making so much of our modern world even possible.
I think this quote from our source material just nails it. It says, "Pile foundations have transcended their historical roots to become integral components in modern construction." I mean, think about that. This ancient idea, literally just driving posts into the ground, has evolved into something that's totally indispensable for modern engineering. It's what lets us build bigger, taller, and in way more challenging places than ever before.
When you really get down to it, that's exactly what these things are. They are the deep, unseen roots that anchor our entire cities. They're what gives everything the stability and the resilience it needs to stand tall. And all of this leaves us with a pretty fascinating question for the future. As our ambitions get bigger and bigger, as we try to build in more and more extreme environments, I'm talking deep sea, maybe even other planets one day, how is this foundational technology going to have to evolve? What will the unseen giants of tomorrow